Okay, today I'm going to explain as much as I can in kind of a short session here about our water world. So many people know that our world is mostly water, 70% water, 30% land mass. So it seems like we have an abundance of water. But I really like this graphic here because it helps me understand really how rare the water is that we drink. So if you're looking at the total global water, 96.5% of it is in the ocean. And the fresh water that we use on a daily basis is only 2.5% of the global water. Of that fresh water, you have 68.7% of it locked away in glaciers and ice caps, and the 30.1% is in the ground as aquifers, and then only 1.2% of that 2.5% here, only 1.2% is on the surface. This is the water that is most easily accessible to the human population. And of that 1.2% of our surface water, 69% of it is stuck in the ground as permafrost, 20.9% of it are in lakes, soil moisture 3.8%, swamps 2.6%, river 0.49%, 2.26% of it is in living things, and 3% of it is in the atmosphere. And I think that's pretty interesting that even though we're looking at very small percentages, how much of a high percentage there is in the atmosphere. Think of all of the living things on the surface of the earth and how each living thing, similar to humans, are mostly made of water. That's only 0.26% compared to the 3% that's in the atmosphere. But even that is such a small percentage compared to the 1.2% here of the 2.5% of fresh water of the total Earth's amount of water. Included this quote by Benjamin Franklin: "When the well's dry, we know the worth of water," for obvious reasons. The main concept that we're going to start off with today is the water cycle. So you've probably heard of the water cycle before, so some of this is probably going to be review, but I hope you get to see maybe a few new things today at the high school level. So water cycle is a repetitive process that has been going on since the beginning of planet Earth. As soon as Earth got water, we also got the water cycle. So all of the water that we drink today has been around for millions of years. The same water that dinosaurs drank, we're also drinking because of the water cycle. So just kind of an interesting way to think of it. So there are a lot of components here, but you'll see you got this back and forth between evaporation, precipitation, and surface runoff, and all of the things in between there. So based on this graph here, I also want to point out volcanic steam, even though it does contribute to the water cycle, is not anything we're really going to focus on today. And other than that, most of the energy that fuels this, other than volcanic steam, comes from the sun. Not most, all of the energy that fuels this comes from the sun. So that big clunky image that we just saw, I think, can really be broken down into three main components. Four if you count the watershed. So precipitation, condensation, evaporation, and then of course the collection of water. So with precipitation, that's simply water falling to earth, either in the form of rain, snow, sleet, or hail. With condensation, that's the ability of water to form as a liquid from a gas. You probably have seen condensation when you take a cold beverage out of the fridge. So you go from that cold environment to that warm environment. That creates basically a dew point inside your house on the surface of the can of Coke or whatever it is you're drinking. This is completely dependent on temperature and atmospheric pressure. Examples of this are dew, clouds, fog, and deposition. Evaporation is the ability of water to go from a liquid to a gas. This also changes with temperature and pressure. Examples of this are steam, transpiration, and sublimation. So you probably have seen evaporation happen if you just set out a glass of water and it gets left out, let's say, overnight. You can even notice the next day that the water level has gone down. If you've never seen that, take a glass of water, you make a little mark where it starts, and check it 24 hours later to see if it's gone down or not. If it still hasn't gone down, that means you have a lot of humidity in your house, which is probably a good thing. And just leave it there for a little bit longer, and it will eventually go down. And if you left it there long enough, it would dry out completely. So the two main concepts here between evaporation and condensation, I think, can be the most complicated out of the water cycle. So that's why we're focusing on these so much. So condensation forms when the temperature hits the dew point. The dew point is the temperature that's just right for water to change from a gas to a liquid. And every day you'll see dew point if you look up the weather for your particular area. So dew point changes not just because of the temperature. There's something else at play here, and we'll get into that. These changes can happen in different layers of the atmosphere. For instance, it can be cloudy but no dew on the ground. So that just means that there's condensation occurring above you but not where you're at. Deposition, we saw that word earlier, is where water transitions from a gas to a solid, so it's like a special form of condensation. The change in temperature and pressure have to be just right. You often see this in mountainous regions, but it can also occur in the Arctic. So we're going from a gas to a solid, totally skipping the liquid phase because of the change in temperature. Evaporation happens all the time, so there doesn't have to be a special dew point for evaporation to occur. Set out a glass for a few days and the water just disappears, like we said earlier. The rate of evaporation, though, increases with temperature. Think about a boiling pot of water. If you increase the energy, the water will evaporate more quickly. So on a hot day, you're going to have more evaporation than you're going to have on a cool day. Evaporation is how water gets into the sky. And the other word, sublimation, I said earlier, is where water goes from a solid to a gas, completely skipping the liquid phase. Again, often seen in mountains and in the Arctic. So, so this would be a quick rise in temperature in a rather cold area. Humidity is a measure of how much water is in the air, so you'll often see a humidity percentage. Usually, if you see a really high humidity percentage, that means that rain could happen, but not always. Depending on where you are, seeing that humidity percentage can tell you how comfortable it's going to be outside. In a hot environment, you certainly do not want a lot of humidity. Humidity is, if you've ever been in any hot Kansas summers, oh man, humidity will turn a decent day into a miserable one. Transpiration is a new word here. It's the evaporation of water through the leaves of a plant. So let's get into that in a little bit more detail. So this is the ability of water to evaporate through the leaves of a plant. It's also called evapotranspiration. You saw that on the water cycle. So this happens due to the cohesive forces of water. Water essentially climbs like it's not alive, but because of this natural property of water, it climbs from the ground to the roots, up the stalk, through the leaves, and then finally into the air. Animals also do this, including us. When we sweat or when a dog pants, they're releasing water that they've taken from other sources back into the atmosphere. Hello, what about the watershed? Did you totally forget about it, Mr. Hogan? No. I just think the watershed's pretty easy to understand. This is the many ways that water collects on the surface by draining from an area of higher elevation to an area of lower elevation. So in our image for the water cycle, you saw the mountain to the ocean. Now, there aren't mountains and oceans everywhere. You know, I'm from Kansas. There certainly weren't any mountains or ocean anywhere near there, but we still had a watershed. Every town probably has a watershed that they attempt to control the flow of the water. So, so let's just talk about that briefly. Water enters the watershed through either precipitation, snowmelt, and potentially even permafrost melt. Water is carried through rivers and streams of many sizes. This could be a super small stream on the side of your driveway or the road, or a large creek. And, you know, obviously rivers vary in sizes from small to very, very large. And then from there, it's collected in either lakes, ponds, wetlands, groundwater through infiltration, and finally the oceans. I don't go through, I'm not going to talk about infiltration too much. This is literally just water filtrating, essentially, through the dirt and rock into what's known as an aquifer. So you'll see aquifer on the water cycle image, and when you do your discussion questions, there will be a question, or there will be a little more information there on your vocab. All right, so just to review real quick, three main components of the water cycle I would like you to have memorized are evaporation, condensation, and precipitation. And then if you can kind of remember here, maybe I should have included a word. You got the watershed. You still have where all the water goes. So water evaporates into the sky, some form or another, condenses either in clouds, and then that condensation comes down as precipitation. That's really the simplest version of the water cycle. All right, so our second main concept today is what makes water so special. So if you'll notice in your discussion questions, I have your essential question is why is water important for life? You know, I mean, we all know that we need water. All animals, all plants need water, but why is it so special? Why not ammonia? Why not something else that's like water? Why not acetic acid? I don't know. So we're going to kind of talk about then the special properties of water that make it special. So the first thing, and I think one of the most important, is the fact that water is a polar molecule. So here in this image, you are seeing an oxygen and two hydrogen. That's H2O. And you got this funny squiggly line here. That's a lowercase delta. It's a Greek symbol. And this is just used to represent partial charge. So delta negative, delta positive. So this is a partial negative charge and a partial positive charge on this side. An interesting fact, this only occurs because of the shape of this molecule. If you think CO2, you got carbon in the middle and oxygen on the side. It does not have this shape, but it does have a negative and a positive side. But because its shape is the way that it is, it does not act like a polar molecule. So just kind of an interesting fact there. So anyway, the important part to understand about that is that basically makes every atom of water a tiny magnet. So you know a magnet has a north side and a south side. And so your north side and your north sides don't connect, and your south sides and your south sides don't connect. But you've heard the phrase maybe opposites attract. North attracts to south, and they stick together. So you've probably seen this before. Well, try to imagine that on the subatomic scale with a water molecule. Each little water molecule is sticking together, negative to positive, negative to positive, negative to positive. So that special property is going to come up later, but it's really one of the most important ones. And being polar allows water to dissolve other polar molecules. So if, let's say, you have sodium chloride and it has a partial positive charge, the partial positive charge is going to connect to the partial negative charge, and it's going to pull that molecule apart, and so it's going to dissolve sodium chloride. So you're going to have sodium and chloride ions floating around in your water, creating a solution, salt water. So then you dry it out, and then they go back together. And anyway, that gets into some complicated chemistry there, and I have to always remember that we are in earth science. So, but really, that's one of the most important aspects of water, is because it it creates the nutrients needed for life by dissolving inorganic material over millions of years through erosion and basically the watershed. Another fact of water is that it's less dense as a solid. And we all know that ice floats on water, right? If you have a drink and you put ice in it, occasionally it'll sink, but that's only because it's like getting stuck on the side of the cup. Without a cup, you got giant icebergs here. They look enormous. They probably weigh a ton, but yet they are still floating on the water. So why is that? Well, as water freezes up, the tiny crystals take up slightly more volume. So remember last week and the week before we talked about density. If density equals mass over volume, remember as volume increases, the density decreases. And as density decreases compared to the liquid water, the frozen solid water floats on top. Oh, and I did want to say, in your discussion questions, I ask you, well, think of a world where that's not the case. And just to point out, this is not common for many substances. Most substances, when they turn solid, they actually become more dense, more compact, but not water. So that's why it's special. Water has a high specific heat. So this concept is kind of tough to simplify, but I think I did an okay job here. Essentially, this means that it takes a lot of energy to create a phase change. Water can stay warm overnight and cool during the day because of this unique quality. So areas along the coast, like Barrow, usually have a more comfortable, stable weather environment. Less storms maybe, other than ocean storms blowing in, because water keeps the atmosphere a more stable, I guess, in that area. So, for instance, you probably wouldn't notice it here in Barrow, Alaska, but the ocean, before it freezes over, if you were to take measurements right now there's not as much sun, but as the sun heats up the ocean, that water in the ocean stays warm overnight. And then as it cools very, very, very slowly. And so during the day, the water is typically cooler because of the previous night. And then at the night, by the time it warms up slowly, it stays warm. So I guess most things don't have this high specific heat. And to compare, here's water as a liquid. Its specific heat is 4.18. Well, what's that number mean? So this is where I think it really comes together for me. 4.18 joules per grams degrees Celsius. So that means the ability or the amount of joules or energy it takes to heat 1 gram of a substance 1 degree Celsius. You've probably already familiar with this concept as a calorie. Calorie we usually think of as the form of the amount of energy in a food. Calories aren't bad. We need calories to fuel our cells. So a calorie, I think, is represented by 1 gram of water per degree Celsius. The energy to heat 1 gram of water 1 degree Celsius is a calorie. So anyway, so that's 4.18. So we're looking at the comparison of the amount of joules. That's 4.18 joules to heat 1 gram of water 1 degree Celsius. As water changes phases, so does its specific heat. So the S means a solid and the G means a gas. So 2.06 joules to heat 1 gram of solid water 1 degree Celsius. And gaseous water, 1.87 joules, the amount of energy to heat 1 gram of gaseous water, water vapor, 1 degree Celsius. So let's go back and look at that. So enthalpy change, we don't need to know that, but this is talking about kilojoules. So that's 1,000 joules. So to go from ice, you have this transition phase where we're raising the temperature, and it doesn't seem to require nearly as much energy to get to this freezing melting section here. But then, as we're in this slurry between ice and water, we wait, no changes at all. We're still 0 degrees Celsius, and that whole process takes, nearly as much as it did to get to this point from negative 100 degrees Celsius. So that's pretty crazy. And then as that slurry finally turns liquid, the liquid heats up, heats up, heats up, heats up. Here we are nearly double what's going on here. And then it stays liquid for 40.657 kilojoules. That's 4.657 times 1,000 joules. So it's still liquid here before it finally. So here we have, boiling is starting to occur here, and then it starts to turn into a gas. So you can see here, this big part here is what summarizes the water's ability to hold on to that heat, 4.18 joules per heating 1 gram of water 1 degree Celsius. And obviously the amount of time that takes to heat, let's go back one more time, the amount of time that this takes is going to change quite a bit, so we don't see time on this graph, but if we were to include time, we would also have to know how many grams we are heating up. The more grams that we have of water, the longer it's going to take. And okay, so that's just water. Well, let's compare that to other things. So ammonia as a gas, I guess here is 2.09. That's a little bit less, or half the amount of water as a liquid. But water as a gas is actually a little bit more. That's kind of interesting. Ethanol is a liquid, so that's like alcohol. 2.44 as a liquid compared to 4.18. So what that means that it's going to take less energy to heat up that same amount of ethanol 1 degree Celsius. It's going to take almost half the amount of energy. So if you were to boil ethanol and water, ethanol would boil a lot more quickly. Aluminum. 0.897 as a solid, that's significantly lower than water. And then you have all these different amounts here, and I'm not going to go through each one. But the lower the specific heat, kind of an interesting concept here, the better it works as a conducting material. That means that it's able to transfer heat very well. And that also is a good property. But not so good for our case here with understanding how water helps with life. Okay, so other related properties of water. So these ones all kind of, I feel like, go together: cohesion, adhesion, and surface tension. So let's break those down. Cohesion. Since water molecules act like tiny magnets, it gives water a high cohesion force. That basically just means it has a high ability to stick to itself. So all substances have this have like a number associated with its cohesion force, and water just has a higher one. Okay, adhesion is the ability of a substance to stick to other surfaces. So adhesion forces is what allows water to be absorbed by a towel. It's also these both are what contribute to a plant's ability to absorb water. Cohesion and adhesion are both at play when a plant is taking water through all of its different parts. A plant can't move, and its cells are pretty much stationary. It's just water doing all the work, and the plant just evolved to allow water to do its job naturally. And our cells do the same thing, but that's biology. We'll leave it alone for now. And then there's surface tension, which is the measure of the ability of a substance to stick to itself before the bonds break. So as you can see, it's very closely related here to cohesion. Water has a high surface tension. So I think the image will explain that though a lot better. So we'll move on. So here's the image I use for cohesion. So if you ever take little drops of water and you keep adding water and water to it, it actually can bead up like this. That's the water sticking to itself. It's not sticking to the leaf here, it's sticking to itself. So I think that's a pretty good image for that. Adhesion, when I look up images for adhesion, oftentimes you'll see it sticking to spider webs. Can be viewed in our science class pretty easily A fun thing that you'll see is, I think they call it chromatography. It's where you basically just take some ink, like from a marker, put it on a paper towel, put it on a coffee filter, whatever, and then you stick the end of that in some water, and you get to see those colors kind of bleed through the rest of the material as the water adhedes, I don't know, is that a word, to the rest of the material. So. And then there's surface tension. Sorry if anyone's really afraid of spiders here. I promise you this isn't going to jump out of your screen or anything. But there are lots of bugs that use surface tension as a... so in this case, it's probably looking for prey on the water, but there's other bugs that can... You've seen water skimmers that can go atop the water that way. And this only can happen because of water surface tension. You can see those bonds aren't breaking. It's like a... I don't know. It's just, this is the best way to visualize it. The bonds of the water aren't breaking. Surface tension, these little water droplets here also could be described just as easily with surface tension. If you fill a glass all the way to the top, you'll usually see kind of a convex bubble on top of a glass of water, and that's the water sticking into itself. The smaller the container, the bigger that bubble's going to look. And I haven't talked about this yet. Viscosity. Can't talk about cohesion and adhesion and surface tension without talking about viscosity. It's the measurement of a substance's ability to stick to itself. This affects a substance's spreadability. So think about honey. Honey can spread, but not very easily. If you were, I don't know, I was just thinking of spreading honey on a piece of bread and then trying to spread water on a piece of bread. You're not going to be able to spread the water because it does not have nearly the viscosity of honey. It also slows down its ability to flow down surfaces and be absorbed and all these different things. And because of water's viscosity, it has just the right amount that it's not too viscous and it's just viscous enough that it flows the way that it does. And finally, hydrogen bonding. This is the big one. This is our twist ending here. M. Night Shyamalan ending. Hydrogen bonding, not really. Okay, when life places stones in your path, be the water. A persistent drop of water will wear away even the hardest stone. Autumn Morningstar. I wish I knew who that was, but I like this quote. So hydrogen bonding is really the answer to our essential question. I mean, all the other stuff is important, but hydrogen bonding is what makes life work. Hydrogen bonds are the bonds between a partial positive hydrogen and another atom with a partial negative charge. So here we are going back to the polar properties of water, which are very, very important. And hydrogen bonding does not exist without polar molecules. But hydrogen's ability to bond easily and separate easily is what makes it a perfect candidate for DNA. So DNA is able to easily replicate because of this bond's ability to easily be separated and put back together. So I don't know how much you know about DNA replication, but what happens here with DNA, so here we have the different, diribonucleic acids. So here we have all of these different things here sticking together, and these, due to an RNA molecule, get separated and copied and put into different parts of the cell. So that every part of the cell relies on the ability of DNA to take itself apart and put itself back together. And that only happens because of hydrogen bonding. And then it answers the question why water behaves the way it behaves. Why does water flow the way that it does and have all those other properties? So almost all of the properties of water are what they are because of the polar hydrogen bonds. Cohesion, specific heat, density, condensation are all affected by the hydrogen bonds. If we didn't have hydrogen in there, water would not exist. I mean, it's kind of goes without saying, you know. Okay, so if you are in earth science, you don't really need to stick around for this last part. North Slope science, I wanted to do a little bit more on vapor pressure and relative humidity, because we're kind of talking about weather prediction. And in order to, I think, fully understand how to predict the weather and understand how weather works the way that it does, I really think it's important that you understand why water behaves the way that it behaves. So a huge part of water, obviously, is evaporation. So earlier we were talking about evaporation going to the air and the dew point and all that stuff. So here we are coming back to that in a little bit more detail. So here is a graph of the saturation vapor pressure measured in kilopascals and temperature in Celsius. As the temperature increases, so does the saturation vapor pressure. So what does that mean? Well, I had mentioned if you have a pot of water and you boil it, that water is going to evaporate much, much more quickly. So that's kind of what's going on here. As we increase the temperature, the water is wanting to evaporate more and more and more. So the saturation vapor pressure is just the measure of that pressure between the atmosphere and the water evaporating on the surface. So for weather predictions, I want to kind of explain these few points here a little bit more. Humidity. So the difference between humidity and relative humidity, honestly, I've spent hours looking into relative humidity. Humidity seems to make perfect sense. This is the percentage of the atmosphere's ability to hold on to water vapor. But so is relative humidity. But where does it differ? Well, it seems that the amount of math that goes into it, I guess. That's really what it seems to boil down to. But I think that the math actually really helps my comprehension of what's going on in the atmosphere. So we're gonna do that a little bit. So dew point is closely related here. The dew point requires the humidity, temperature, and pressure to all be just right for water to condense. So if you see a dew point on your weather prediction app or whatever you're using, that means at that temperature, the amount of water that's in the air at that temperature, at that pressure, is going to turn into water from the air. It's going to condense into little water droplets, wherever that happens to be, either in the sky or on the surface, at that temperature. And that temperature changes, that dew point changes all the time. And then there's relative humidity, the amount of water vapor present in air expressed as a percentage of the amount needed for saturation at the same temperature. That's literally the Google definition. I'm having a really hard trying to simplify relative humidity. But this, I think, does the best job. This is a simple equation. Relative humidity is equal to the actual vapor density and this over the saturation vapor density times 100%. So that's just turning it into a percentage. Okay, so what does that mean? Well, so here's our relative humidity percents. We're going down. So what's causing this to go down? So the temperature and these three things here, it stays the same. We got 10 degrees Celsius, 10 degrees Celsius, 10 degrees Celsius. And then the dew point goes from, this is the ability again for water to turn into water from the air, is 9 Celsius, 8 degrees Celsius, 6 degrees Celsius. So we're going down in dew point. And so as we plug in the calculations, our saturation vapor pressure is 9.21. Our actual vapor pressure is 8.61, and then you do that little division thing there that we talked about, and you get 93.49%. That's your relative humidity. So that's the amount of water that is in the air. The percentage of the water that's in the air that can be in the air or is in the air. I don't know, but really what you need to know is that it is a measure of the amount of water in the air. So explaining the difference between vapor pressure and saturation vapor pressure here, I think, is going to help. But let's move on. So as the dew point lowers, so does our actual vapor pressure. So our pressure is lowering it. It's basically evaporating less and less. So even though our regular temperature is staying the same. So how can temperature stay the same and then our dew point changes? So our dew point changes because the amount of water that's in the air is changing. As the amount of water in the air changes, the ability of water to condense also changes. So if there's less water in the air, the dew point is going to be lower, which means that our relative humidity is lower. Okay, is it starting to come together now? So to kind of review these things here, in the simplest of terms, our saturation vapor pressure is the potential of water to saturate the air. That's 100%. If all conditions are right, that's as much water could be in the air at that given time based on the current temperature. And then the actual vapor pressure is literally just the measure of the actual water in the air using a special tool. So we get our actual vapor pressure from the dew point, just plugging in the numbers. Okay, and then our relative humidity, honestly, once you understand these two, I think is pretty simple because it's just division and then a percent. The percent of the water's potential to saturate the air. So if we go back here, thinking about the percent of the water's potential to saturate the air, that means here, with a higher dew point, the water has a high potential to saturate the air. That means it's probably going to form some clouds. It's probably going to rain that day. Okay? So let's step away then from the difference between saturation vapor pressure and actual vapor pressure, because this is literally just, again, the potential and then what we're measuring. So let's look, though, at vapor pressure. Maybe you've never heard that before. You probably have never heard it before unless you've taken chemistry. So this is my best attempt to clarify vapor pressure in a nutshell. So after scouring the internet today for such a long time, I found this guy here that did this neat little graphic. So let's just go through it. All fluids want to reach an equilibrium. Okay, so water is definitely a part of a fluid, and it wants to reach an equilibrium. So when we were talking about weather before and air masses and high pressure systems moving to low pressure systems, that's because of every molecule's innate desire to reach equilibrium. Okay, so water is a volatile substance, which means it evaporates easily. So the air-water intergaseous water. So at the air-water, intergaseous water, and liquid water come into contact. That doesn't seem like it's written very well. But basically, the more evaporation that occurs, the more gaseous water there is. So as temperature goes up, these evaporated molecules push against their surroundings, which is vapor pressure. It's the water's ability to push up as a gas naturally. And if you remember, evaporation is always happening. So more evaporation happening means there's a higher vapor pressure. But the water molecules can also go back. And in a closed system, we'll reach an equilibrium where the rate of leaving evaporation equals the rate of returning condensation. So there's no net change in the number of molecules in the different states. So when we're talking about vapor pressure like Earth is, kind of a closed system, but when we're looking at, let's say, a city, and we're looking at the amount of water's ability to evaporate and condense and all of these different factors for weather, this vapor pressure number tells us quite a bit of what's going on in the atmosphere. So to me, the best way to really understand that was to think of water boiling. So I'm gonna continue on that path here. So when this vapor pressure reaches a point where it equals the external pressure, it boils. So as pressure on the outside, atmospheric pressure, thinking of all of the tons of air that are above our head, it's also pressing down on our cup of water. And that water, though, naturally wants to evaporate as well. All liquids want to evaporate, and they're looking for this equilibrium here. But once it reaches that equilibrium, either by increasing the temperature or decreasing the external pressure, which is atmospheric pressure, affects the water's ability to evaporate. And also, he had a lot more information on his page about surface tension and hydrostatic pressure. We don't really need to talk about that. But surface tension does affect the bubble formation in boiling water. Anyway, at the temperature at which this occurs is the boiling point. You probably know different altitudes have different boiling points. So if you're in Denver, Colorado, the Mile High City, you have a lower boiling point than you do here, which would just simply be 100 degrees Celsius. But in Denver, it'd be like, I don't know, 95 or something. Temperature is an average of kinetic energy, energy of movement, so the boiling point's a measure of how much energy molecules in a certain liquid need to vaporize at a given temperature. So anyway, just thinking of water wanting to constantly leave, but then it is also pushed back, and that balance between the two is our vapor pressure. Okay, so why even bother explaining this at all for our North Slope students? Predicting the weather requires at least a basic understanding of the properties of nature, water being one of those properties, or one of those properties of nature. The amount of water in the air greatly influences the local temperature, pressure, and precipitation in an area for weather prediction. And that's important for North Slope students, especially because weather prediction here is not very good. There isn't a barometeorologist, so everybody, I think, needs to try and understand the weather so that they can predict it on their own, especially when you're out boating or hunting. It's also a major component, though, in climate change, and climate change affects North Slope a lot. We experience climate change like 2 times the rate of the world because of other things that I've explained in the past. There are no greenhouse gases as powerful as water. The more water in the air greatly impacts the Arctic climate, and as the Arctic warms, so does the rest of the Earth. So when I was in college and I learned that water technically is a greenhouse gas, that just blew my mind. Because you don't think of water vapor as a greenhouse gas, but it is. And the reason why CO2 and all of this is an issue is because it increases water's temperature, which increases its saturation in the air. And the more water that's in the air, the more heat is trapped on Earth, and it becomes this like repetitive thing, and it's just scary. Anyway, that's it. That's it. We went through a lot of information today. Vapor pressure for you North Slope kids, relative humidity, dew point, hydrogen bonding, viscosity, surface tension, adhesion, cohesion, specific heat, density of water, water being a polar molecule, water cycle, evaporation, condensation, precipitation, and the watershed. A lot of information. So just want to say thank you all if you've made it all the way here to the end for watching. I hope this helps you with not only your discussion questions and your quiz, but I really believe that through science there can be a lot of change that happens in this world, and I hope that this helps you. Anyway, if you have any questions, I'm always here on Google Hangouts and Zoom every day. So have a great day.